Hi, I'm Ben-Yaakov. This presentation is entitled SPICE Inner Working and the Simplest Way to Import Sub-Circuit Models. In this presentation, I'm going to talk about the SPICE program organization, show a block diagram, essential files, model types, and then I'll show what I think is the simplest way to import third-party components. I'll show some simulation examples, and eventually I'm going to compare some of the simulation results with datasheets. So let me start with some history here. Now, SPICE was developed around 1974 at Berkeley by Lawrence Nagel. Actually, it was under the direction of Professor Donald Pedersen. Now, being developed by a federal government grant, the program was actually made public domain. Now, the basic problem includes the simulation engine with very little graphics, or actually with no graphics for input and output. Now, the input was fed via punched cards, while the output text was printed on a teletype. And the plots, if you can call them, were drawn by actually dots or asterisks printed on a teletype. So it was really very simple, but very effective, and the engine, the simulation engine, very, very powerful. Now, being public domain, companies, and actually I think it started with Microsim, they adopted SPICE basic program and then added some interfaces, and in particular they added the schematic capture graphic and then an auto graphics so that the results can be shown on what is called the probe. And then Cadence got the rights to PSpice. Now, many other companies developed simulator using the Berkeley engine, the basic simulation program, and one of them is LTspice. Now, the many companies that adopted SPICE actually retained the Berkeley core to a very large extent. There's been some addition, but the main idea and the main algorithm has been retained just about as it was developed in 1974 at Berkeley. Now, in this presentation, I'm going to emphasize the LTspice derivative of the SPICE family. So let's have a look at the general outlay of the simulation program LTspice. Now, we have first of all the schematic capture. This is where you put your circuit diagram. Now, when you run it, the first thing that is done is LTspice will convert this graphic representation into a netlist, okay? And then it will bring in models that are specified from a library or from a model that you have in your own computer. Then the program will run, and the algorithm is carried out by the modified SPICE core. The output data is then put into a file. In the case of LTspice, is a .raw. Then there is another file which gives you some information about the run itself, the progress of the run, the time it took, and some information. In the case of PSpice, there's actually a .out file that is much more comprehensive. Now, the data that has been collected throughout the simulation can then be displayed on this graphic interface, which is generally called the probe. And this is the general organization of the program, very similar to other SPICE-based programs. Now, the program is using models. Components, devices, like diodes, are specified and dealt with by the so-called models. Now, there are models which are intrinsic in the simulator itself. That is, for example, the equation of a diode, or BJT, actually it's a Eber-Small, a modified Eber-Small model, are embedded in the program itself. There's no access to a user. The equations are in the program, and what the user can do is actually just feed in the parameters of these equations. So there is a .model file that includes all the parameters of this equation, and the designation of this file is usually .lib, although it could be a different designation. And there's another type of model, which is the subcircuit, which is actually an electronic circuit that emulates a behavior of a component or a circuit or a block, like an operational amplifier. It could be single component, like an IGBT, operational amplifier, and in a more complex system like a DC to DC converter. Now, this subcircuit is actually a netlist file, which has the ending of either .sub or .lib. There are some other designation of this file. Now, the files of the model are normally stored in the .lib folder of LTspice. LTspice program has a number of folders. One of them is this .lib, or if you are importing it, you can put it actually anywhere you wish, and this is what we are going to talk about later on. Now, here I'm showing an example of an intrinsic model. Now, this is a NPN transistor 2N2222, very popular. So this is the file that includes the parameters of the equation of a BJT N-type NPN, and the equations themselves, again, are within the simulator. So these are just the parameters of the equation. This is like the leakage current, for example, and there's many other parameters, which are then used in the calculation during the simulation. And here I'm showing a subcircuit. This subcircuit, this particular one, is of a optocoupler. So we see that it starts here with the subcircuit. This is the name of the device, 4 and 25. And these are actually the terminals, okay? Here it is, 1, 2, 3, 4, 5. These are the interconnection between this subcircuit and the outer part of the program, of the circuit. And it is a netlist, meaning that you have here the components and then the nodes to which these are connected and the values. So this is like a resistor, R1, connected between the N003 node to node number 2 and a value of 2 ohms. And this is a diode. Now, in the subcircuit, you can have intrinsic models like a diode or a transistor. Here we have both a diode and a transistor. Here is the diode. Again, this is a diode between node 1 and this node N003. And this LD is the name of the model. Here is the name of the model. And these are the parameters. Now, there are only few parameters, because if you don't specify the parameters, they are left in the default value. There is always a default value to the parameters. So we have a diode, we have a transistor, and then this is just the end of this subcircuit. So what I did, I just looked at this netlist and reconstructed the circuit corresponding to this netlist. And what we see here is that we have between node 1 and this node a diode, and then we have a resistor, and then we have this G is a voltage controlled current source, which is connected to the base of the transistor, so that we are injecting current into the base, which is a function of the voltage across the resistor, and then of course the current of the collector to emitter is an amplified value of this current. So this is actually an emulation of a real optocoupler with this specific behavior of the 4 and 25, and here is actually the gain of the voltage control current source. So this is the idea of the subcircuit. Now, associated with each device or component, we have a symbol, okay? Like here is a symbol of an operational amplifier. Now there is a file. In the case of LTspice, it ends by .asy, and this is the symbol file. And here there is a script which actually describes this symbol, including all the wires and the terminals, as well as the writing here. For example, here is this number of the device, and then also the description of the device. When you sort of click on it, this will come out. So this is actually the symbol of the device. So when you draw a schematics in LTspice, there are models which are associated with a symbol, like in this case an operation amplifier. Now the LTspice program, as you download it, has many components and devices already built in a library that you can look at by the search of a component. However, many times you like to bring in a component or a device which is not available in the program itself. Okay, a new silicon carbide transistor, another GaN transistor, another device, another operation amplifier. So the question is, how can you incorporate a model which is coming from a third party into your program that you are running? Now I'm demonstrating a method which I think is actually the simplest one. In this method, we are not creating a symbol specifically for each of the models that we are importing, but rather using the built-in ability of LTspice to self-generate a simple symbol, so that we don't have to bother about really drawing a symbol with all the terminal and the shape. And this is actually the simplest way to go. So you start off with having a file with a model. For example, here is a silicon carbide MOSFET, and this is the file that includes the sub-circuit model of this transistor. So you have to locate it, you have to find it, and then to bring it to your computer and store it somewhere. It doesn't matter. Now, next thing you do, you just upload this file, this sub-circuit file, into LTspice. Just by file, look for the directory, and then upload it into LTspice. Now, the file is a text file, and here you can see what it is. Now, it starts here. This is a Wolfspeed silicon carbide MOSFET, and here is a description and some basic information. Now, when you have a dot or asterisk, this means that LTspice ignores this line. Okay, so these lines are just for information, just explaining what it is, what transistor it is, etc., etc. And then you can scroll down and you can get to the actual sub-circuit. Here it is, it's hidden here. Here it starts here. And then here is the netlist of this sub-circuit. So the next thing you do, you right-click this sub-circuit line, and you get this window coming out, and choose the create symbol here. Then you get this window asking whether you wish to automatically create a symbol for this particular device, and then you say, of course, yes, and here it is. So LTspice actually created a very simple, like a block symbol for your device. Has in the terminals, it knows how many terminals and what type of terminal it needs, because they are specified in the sub-circuit, as we have seen earlier. Now you can move around these by this handle here. You can move it around so it'll be more convenient, and the location will be more appropriate for your drawing of the schematics. Here it is. I moved the drain up, the source down, and the gate here for this MOSFET. So we are ready to go. Now what happened is that this device now is within the components of LTspice, so you can look for it. Actually, if you write the model number of it, you can get it directly. Here it is. Or you can go to the auto-generated folder within this library, and here it is. You see, these are the sub-circuit that I've uploaded, and you just choose the one that you wish. When you do this, it's like any other component you've chosen from this component storage of LTspice. So here is an example. This is a IGBT that I brought in from Infineon. This is this IGBT, Here is the gate, this is the emitter, and this is the collector. And they recommend, Infineon recommend to do some changes to the option of SPICE. By the way, all these options are original with the Berkeley simulator. Okay, it's nothing new here. So you can change these options because probably they do have some convergence problems. So they are relaxing the resolution of the simulation. And I'm running now a simulation to show the output characteristic of this IGBT. Okay? What is done here is the gate voltage is changed in steps, and then we have a sweep of the collector voltage via this 1 ohm resistor. So here is the result. We have here the gate voltage. Here it is. This is the current, and this is the collector to emitter voltage. Very, very typical, of course, of a MOSFET, and we see that the model is running pretty nice in this respect. Now if I sort of zoom in, this is now comparing the simulation result with the datasheet, which shows the collector emitter voltage up to 3 volt. I have it here also, and then 90 amp here. And this is from the datasheet the 7 volt, and this is the 7 volt from the simulation. Pretty good. Well, the 8 volt is a little bit off, but in general I think it's not too bad. And here is another example. I brought in a silicon carbide MOSFET, and I've built here a circuit which is basically a double pulse test. That is, we have 2 transistors. This one has a gate to source voltage of 0. Okay, this one is getting a pulse from here, the gate here, and then I have an inductor. So when the pulse is coming in, the first pulse, the current of the inductor will build up, and then when the pulse here or the voltage here goes down to 0, then the current will be flowing through this transistor, and the next pulse I'll be turning on this transistor under hard switching because we have a current here through this device. So I can see the turn on and turn off of this device under hard switching, which of course will tell you about the characteristic of the device and its behavior in the switching domain. So here what I'm getting from the simulation, this is the pulse, this is the gate after the gate resistor. This is how the inductor current is building up. Here the pulse is down again, the gate voltage is 0, then the current is just about 0. It's a little bit discharging, of course, because it's a short on the inductor through the upper transistor. And then I have the next turn on. I'm not going into all these details because this is the outside of the scope of this presentation. Now let's compare some of the simulation result to the datasheet. I'm looking now at the midpoint that is actually the collector of the lower transistor, and during the on time I see the voltage drop across RDS on. Okay, the current goes up to 30 amp, so at 30 amp I have a 3 volt across the RDS on, which means that the RDS on is 100 milliohm simulator. Now the datasheet says that it's a maximum of 80 milliohm, so it's a little bit higher than the datasheet, so it's not that bad. Now I'm looking at the voltage at this point here, or this point here, at the time after the first pulse. That is when this transistor is not conducting, so the current is now circulating here. Now what I see here is actually the drop of the upper transistor. Okay, so this is the 300 volt, this is the supply, and the current is going this way, so this voltage here will be higher than the 300 volt, and in this is what I'm seeing. This green line is 300 volt, and the actual voltage is 5 volt above it. 5 volt is quite a bit. Now if it would have been a silicon MOSFET, we would have an intrinsic diode, and we'll have a drop of a diode, will be like 1 volt, or a little bit higher than that. Now this is not a silicon diode, this is a silicon carbide diode. Now in the data sheet, Cree, or Wolfspeed, is showing here a diode. They're saying that there is a diode here. Well, if this would have been a, say, a silicon carbide diode, then the voltage across it would have been like 1 volt or 2 volts, not 5 volts. So what does it mean? Well, they are saying that there is fast intrinsic diode. Okay, well, what does it mean? So let's have a look at the data sheet and see they have here the curves for this is the current and this is the voltage in the so-called reverse conduction of the MOSFET. That is exactly the situation we are here. There is a current which is going from the source to the drain. Now, as it turns out, the voltage drop, which is this one, is a function of the gate to source voltage. Now, we have a gate to source voltage of 0 volts. The current is 30 amp, and indeed, in the datasheet, they are showing here 5 volt. This is what we are getting. But this is not a voltage drop on a diode. This is a reverse conduction of a MOSFET. Now, you'll see this voltage drop during a dead time, because during normal operation, you either turn on one transistor or the other transistor, except for the dead time. So during the dead time, you're going to see, in a PWM, you're going to see a voltage of 5 volt. The power dissipation will be much higher than that of a regular diode. So you have to take it into account as part of the losses of the circuit. So this brings me to the end of this presentation. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.